Hello guys, welcome back for the second video of the Triton Server series. So we have a new challenge. So we'll be going through this exercise for this week wherein we'll try to deploy three different models. One is going to be a simple image classifier, and we'll deploy this in GPU, and another being a sentiment analysis, a rule-based, keyword-based sentiment analysis, which can live in CPU without harming our inference. And we'll also have TinyLlama, right? So last week I showed you how to deploy TinyLlama in the GPU and have that benchmarked. It is going to be just one model, but this time around we'll have three models. The image classifier will have a format of ONNX, right? I'm pretty sure most of you know about ONNX, but if you are little skeptical about what is that, this is it, right? Go to this ONNX.ai. It is again a neural network exchange wherein you build your neural network in one format, and we can have it interoperable with different platforms. So let's say that you develop your model using PyTorch, and you can have that interoperable with ONNX format with Triton Server, TensorRT. So pretty much right, most of the backend, the ONNX project should be able to support. But I'll have you research about ONNX on your leisure time. But what I'm trying to tell you is we'll have three formats of models that we will deploy this time. One is going to be an image classifier ResNet model that is trained on ImageNet, and that will exist as ONNX, and another being your TinyLlama, which we'll download from Hugging Face, and then we'll have a sentiment classifier model, which is rule based. Now think of ONNX like a PDF, right? Let's say that you write a document, and what you do is you save that, let's say, as a PDF. Now that you've saved that in PDF, you can send this to anyone in an email. And let's say that you use Windows and they use Mac or Linux for that matter. They should be able to open up the email, download the PDF, and they should be able to view the content of the PDF. Similarly, you build your models in one format and have that, you can convert them into an ONNX format, and then people should be able to open or use the model in the platform that they prefer. So this supports most of the platform, right? So this is I think the best analogy that I could give you as far as ONNX is concerned, but please do your research. Now I'll show you the project structure. I've already set up the Docker environment for the Triton server, which I showed you last week. So if you're not aware about that, please go check the last week video, and you should be able to see how I've downloaded the NVIDIA image, Triton server image. And this is the project structure that we'll have for this particular week's exercise. So you can see again I'm using Jarvis. One more thing, right? I'm still using Jarvis Labs, and I'm using L4 system, right? And this has GPU in it. Maybe I'll show you, right? So NVIDIA FNSMI, you can see, right? So it supports CUDA deployment. The CUDA version is 13.0, right? The driver version is 580. And you can see that I've still not inferred anything. So you can see I still have a lot of capacity. So what we'll do is we'll have three models. I'll show you each of these models. If you go to model repository, this is the project structure. You can see I have image classifier, and if I open this, right, you can see it is actually model.onnx, right? That's a format that I was talking about. And if you go to the config, this is actually where your image classification configuration exists, right? So we've set the maximum batch size as 8, the input IDs to be this is the dimension. So it will read the color image. So we'll be doing inference on this image, right? This is a sample image that I downloaded, but you can see it would accept 24 cross 24 cross 3 for the channels, right? And you can see for the output it is going to spit out a tensor that is of dimension 1000 meaning 1000 classes, right? And you can see that we are deploying this in GPU. All right, so this is for the image classifier. I'll also show you the sentiment classifier. So this is the model file. You can see this is a very simple model that works on keyword. So let's say that your environment requires you to have some sort of a rule-based model, a model that works on heuristics, which is not probabilistic in nature, and it is most of the time deterministic. You wouldn't need a lot of tensor operations for it, right? You don't have to use GPU for this, right? I'm pretty sure most of you would have worked with different models, and if you want different models to coexist together, but not all models would require GPU. And this particular model, this sentiment classifier, which is based on keywords, would have its inference in CPU, unlike the image classifier and TinyLlama, right? So you can see, right, I'm actually looking for very few specific set of words based on which I'm doing the classification, right? So this is the whole model file. There you had the model file as an object, ONNX object. Here we have the code since it's keyword based, and you can see that this is going to be the config. Right, it will accept a text, right? Since it is text and since this is keyword based, the dimension is going to be scalar. It is going to accept an array of string, right? And it is also going to output an array of string, and you can clearly see it is going to run in CPU, right? Very simple model. And then we'll come to TinyLlama, and this is TinyLlama. This is a code which is very similar to what we did last week, except the fact that I had the ensemble type of deployment. When I say ensemble, we had a model for tokenizer, we had a model for doing the GPU inference, and then we had detokenizer, wherein tokenizer would operate in CPU, the model inference would happen in GPU, and again the detokenizer, which is again a lookup table, will happen in CPU. Unlike that, I've made everything into one code. I've not used an ensemble method of deployment, but I've used it here in one single code, right? But the ensemble method is much more robust, and that is much more production style deployment. This is just for lab. I just wanted to give you guys an idea of how to deploy multiple model in the same GPU and have turns in terms of inference, right? So having said that, I'll show you where the tokenizer is pushed to CPU and where the inference whereas inference being pushed to the GPU, right? So you can see that I'm using TinyLlama model here, which I'm downloading from the Hugging Face, right? And you can see that yeah, you can see that it is getting tokenized here. Once it gets tokenized, wherein it forms numbers using a lookup table, and then you can see that the input is then being pushed to CUDA. So the tokenization itself doesn't happen in GPU, but once the tokenization is done, it is then the matrix is then pushed to CUDA for inference. You can see that I'm using the maximum generation of tokens to be 128, and just to increase the randomness in the output, I've set that as 0.7, and top probability for sampling being 0.9. And then you can see that the tokenizer.decode, which is detokenization, again happens in CPU, right? It doesn't happen in GPU, because you can see that it is not having the CUDA component while it is doing the detokenization. And then I'm returning the response. This is the whole code for the TinyLlama. So I'll also show you the config. You can see it is going to be type string. String input is what we'll be giving, and type output is also going to be type string, because we'll do the detokenization as a part of model pi itself, right, which will have one. But you can clearly see all of this. I mean, the most of the deployment as far as the inference go happens at GPU, right? Again, you don't have to worry about this configuration. I'll release this as a lab manual, and you can go through the description of the video, and you should be able to see the link for the lab manual, and you can practice this with your own settings. Now, having said that, what I'll do is I'll start the Docker, right? Docker image. You can see that the entire project I have Dockerized. So this is the Docker script, right? You can see. Once I start the Docker, you should be able to see, in live as to what happens when we do the inference. You can monitor the GPU utilization. You can even connect, right? So this 8000 port is specifically used for health check. You can connect this to a Kibana dashboard, a Grafana, or a Prometheus, right? If you are doing monitoring in real time, if you want to understand how your infrastructure performs at scale while doing the inference, this is the port, right? You can do a curl, and 8000 port is exposed specifically for your health. And then we have 8001 and 8002, which is used for HTTP and gRPC. Right, let's say that you wanted to do a streaming of tokens when your model in itself is auto regressive in nature. We use the gRPC, where it will stream one token at a time, so that you don't have to wait for the entire generation to happen to view the content. As and when you can see the tokens, you will be able to digest them, right? That is when we'll use gRPC. And HTTP API, we generally expose this to, let's say that you want to have a third party application which would consume the inference of your model. You generally expose that as a HTTP service, and these are the ports reserved for gRPC and your HTTP. So having said that, what we'll do is we'll start the inference, we'll start the Docker, and we'll basically monitor what's happening, and we'll also benchmark all three models. Okay, so I'm starting the Docker. You can see that I'm starting it as Triton Lab is the Docker name, and you can see that everything is in GPU. The inference would happen in GPU, and you have the 8000 port, 8001 and 8002 port, just like what I explained a couple of seconds back. So let me start the Docker. Right, so you can see all three models are successfully loaded, right? Yeah, and what we could do is so if we do Docker, yeah, you can see that it is started. The Docker has started. What we'll do is we'll get into the Docker itself, right? Because these requirements that you see, okay, maybe I'll show you. These requirements that you see, it is all part of the Docker file, and probably if you run this from your host machine, you will have dependency issues, because all of these are getting Dockerized, and within the environment of the Docker, all these dependencies are resolved. So I would suggest you get into the Docker bash and then try running all the test commands, right? So that's that. So you can see that I'm getting into the Docker shell. So I'm getting into the Docker bash. You can see that the workspace has changed. So right, from Jarvis Labs, I'm inside the Docker. And what I could do is I could just benchmark all the models. All I need to do is, okay, maybe what we can do is we can also watch, yeah, we can also watch the inference, right, as and when it happens, and also the GPU utilization, right? So yeah, so right now we don't have anything, but while we are doing the inference, you will see that this would change. So let's say okay, maybe even before that, right? I'll show you the benchmark code, right? This is a custom benchmark code that I created. You can see, yeah, so we can see that first the CPU inference would happen, and then what we would do is we would go to the image classification. Again, I'm sending the same image file. It doesn't matter because I just wanted to test the Triton server backend for inference. But if you have multiple images, you can also iterate through all of them, and then send that as a batch. We would accept batch size till 8. Right, and you can see that we are doing the inference, and yeah, so this is where we'll be benchmarking, right? We'll basically say how much of batch we should be able to handle per second, and what is going to be the image, the class, and the confidence score. And finally, we have the TinyLlama, which we have deployed in GPU, and we'll send the text, and we'll have that inferred, and we'll see how many words it generated per second. So that is the profiling that we'll be doing across all three models, right? So let me run it. Yeah, you can see, right? It is performing all three inference, right? We've been watching, and yeah, so the GPU is also getting utilized, right? So maybe I'll show you the benchmark itself. Yeah, so we are done with the benchmark of all three models. You can see for the sentiment classifier, it took 29.86 milliseconds, and for a batch size of 3, right? I was telling you, right? So I'll be inputting the same images, and we took 3 iterations of that image, and therefore you are seeing batch size, comma channel, and then 24 cross 24, which is the image dimension, and you can see batch size into 1000, which is the number of predictions, right? We'll have 1000 classes since it is trained on ImageNet data set. And you can see the inference time is 316, and it is the throughput of it is 9.47 images per second. And you can see for image it's saying class 258, right? If you go to the ImageNet dataset, and these are the class IDs 258. Okay, I don't know what is this. So my so let's put it here. Yeah, so my I think it's a dog, and I think that is what we have here too, right? You can see, isn't it? So it is classifying it, right? Now if I do this again, right? Okay, so I also have the GPU benchmarking. So the total latency is 2.14 seconds for generation. You can see it is generating approximately 50 watts per second, right? It happens in GPU. So I've asked about quantum computing, and it has generated close to 128 tokens, because that is what we were limiting the model to generate, right? Now you did see that it's 49.94 and 9.47 image per second, um, right? So again, I'll do the benchmark. Yeah, you can see, right? It is getting changed. So when we are watching it, it again completed it. So yeah, yeah. So when the GPU is free, last time around it was 9.47 images per second. This time around, you can see it was able to do 430.66 images per second. So it really depends on the availability of the GPU. So, and it also depends on how much load you put, right, in terms of sending your input. right? Although it was the same, right? But it really depends on the tensor operations that it is doing and the availability of it. You can see such a large throughput from last time, right? It was just doing, I think, 9.47 image per second, but this time around it's 430.66 images per second, right? Even the words per second, it was 50 words per second last time, it is now 77.58. so if the GPU is really free, you will be able to have a higher throughput. It depends on the infra availability. So that is what I wanted to give you guys for this week as a lab exercise. Please do practice it, and if you have any doubts, right, please do let me know on the comments. I'll be very swift and prompt in responding to your doubts. Thank you.